I am Matteo Bonetti. I am the second year of my PhD at the University of Como, and my supervisor is Francesco Arte, that was here last week, but I can also benefit from the great help of Alberto. And Enrico Barauso. So I just start teaching the framework in which my work is embedded. The standard cosmological model predicts that the large scale structure of the universe is dominated by the dark matter. Yes, of course, the dark energy, but for the structure we have in mind, galaxies and so on, the dark matter is the fundamental one. And the growth of this structure proceeds in hierarchical way.
Matteo, can you use the second one? Thank you.
Please.
Thank you.
So, less massive halos of dark matter merge during the cosmic time to form more massive one. Galaxies are thought to form in these halos, and because of this merger, this hierarchical formation of structure, we can have the merger of galaxies. So, galaxies merge. If we focus on single galaxies, we know that the central region of this letter are characterized by a strongly electromagnetic but also dynamic activity. And the responsible of this activity are thought to be the massive black hole. So, galaxy host massive black holes. If we put together these two things, we are led to the formation of massive black hole binaries. So the real question is now, can this binary merge? Can they represent a source of gravitational waves? So the standard scenario was depicted last week, what also this morning, but I just remember. This is depicted also in the 1980s by Began, Albert, and Rees. So after the merger of two galaxies, we have the first phase of dynamical friction, in which the black hole sinks toward the center of the merger remnant. Then, when the dynamical friction becomes inefficient because of the binary actually beings, in this phase, the black hole starts dominated by the stellar distribution. The dominant process that can harden the binary is the stellar hardening that proceeds the scattering of single star by the massive black hole binaries. This process is strongly linked by the stellar distribution, because this process ejects stars from the center of the galaxy, and therefore without stars the binary cannot harden. Moreover, this process shrinks the binary, and the cross-section of this binary become lesser and lesser. So this process is highly inefficient and can the age of the universe, and the binary cannot reach the third step of this evolution, that the gravitational waves driven evolution. So we need another process to fill the gap. And this historical denote as the last parsec problem. So,
what is T?
Sorry?
T? No, the vertical axis.
T is a time scale associated
Oh, it's time scale.
with the process. Various solution to solve the last parsec problem was presented during the year. The first, for example, the presence of gas can solve the problem because the gas can exert an efficient torque on the binary to extract energy and angular momentum and let the binary to coalesce. For more detail, ask for Felipe or Lupi. A second solution can be the triaxiality. It is likely that during a merger of a galaxies, the merger remnant can present us some sort of triaxiality. And this one can generate a family of centrophilic orbit of the stars that can refill the reservoir of the binary, and therefore the RNA process doesn't stop, and can lead the binary to a scale where the gravitational waves are efficient. Another solution can be the three-body interaction. That is the focus of my work. In the same way as we deducted the formation of a massive black hole binary, if we have more mergers of galaxies that, as Alberto explained this morning, can be and if every galaxy hosts a massive black hole, we are led to the formation of massive black hole triplets. These are a special kind of triplets. They are in a hierarchical configuration. In general, the three-body interaction is chaotic and it's a very rich phenomenology. But the case of hierarchical triplets has a peculiar mechanism that can take place. And this is the Kozai-Lidov mechanism. Mechanism. When I'm considering hierarchical triplets, what I have in mind is essentially two separate binaries. An inner one, that is the binary that is stored at the center of the galaxy, and a third body that forms the outer binary, that is the third body and the center of mass of the inner binary, that forms when another galaxy merges towards the first merger. If the relative inclination of these two binaries is high enough above a threshold that is 39 degrees, this mechanism can be efficient and can excite a large oscillation of the relative inclination and eccentricity of the inner binary. So if we have the inclination grows, the eccentricity lowers.
What's the scale here? For example, inner binary and the outer one.
What is the scale?
Yeah.
To be a hierarchical triplet, the semi-major axis has to be a ratio of maybe 8, 7, 8. It depends on the eccentricity.
But what do you assume, for example, size of inner binary? Where you basically stop?
For the inner binary, what I have in mind is 1 parsec.
Cross.
Because it's the last parsec from the last parsec where we have to. It depends also on the mass of the black holes. For example, for a black hole of 10 to the 8 solar mass, 1 parsec is more or less the scale where a binary stall in the picture that I described. If the black holes are 10 to the 6, the scale where they stall is much lesser. Okay. So the Kozai-Lidov mechanism can excite this oscillation, and in the Newtonian approximation, without any relativistic correction, the maximum eccentricity that the binary can reach is given by this approximative formula. So if we have very inclined binaries, they can reach the inner binary can reach a very high eccentricity. So this is a good thing, because as we know, the higher is the eccentricity, the more efficient is the gravitational waves emission. However, there is a bad aspect of the Kozai-Lido mechanism. It is destroyed. Yes.
So this estimate is very conservative, right?
Yes, of course.
It neglects. So if the outer perturber is eccentric, or if you include the effects of the octopole moment, then the maximum eccentricity.
So in this simple explanation, I'm considering the quadruple approximation. Yes, it's very conservative. If you have if the orbits are circular, you can lower this ratio, and the triplet is stable. For what I know.
You're asking about the maximum
max.
The maximum eccentricity can be much higher.
That's
Yes, sure, of course. Including the octopole terms, it can be much higher. Yes. Sure. This is only for the quadruple approximation. The bad thing is the precession. If the binary precess with a time scale that is much shorter than the typical time scale of the Kozai-Lido oscillation, these letters are strongly suppressed. In particular, this precession can be off. For black holes, it's the relativistic precession. The oscillations are suppressed, but because essentially the precession destroys the coherent piling up of the perturbation of the third body. And maybe I can show you an example. This is only Newtonian dynamics. As you can appreciate, there is a very high eccentricity at the cited 0.98. And this is with the relativistic correction. So you can see that the eccentricity that is inside is very low. So this is a problem, but the relativistic precession is a real fact, so we have to take it into account. So, for my PhD project, what we have in mind, our goal, is to simulate massive black hole triplets in galactic nuclei and discover if the Kozai-Lido mechanism is a viable channel for the merger of massive black hole binaries. How? We have to integrate a differential equation, of course. So we have chosen a high accuracy integrator and to integrate the 18 differential equations that characterize a three-body interaction. The dynamics that we have in mind is the Newtonian one plus the relativistic correction till 2.5 Pn order. These first two guys are essentially responsible for the apsidal precession of binaries. Right.
Is the 2pn actually necessary? I mean, the 1pn introduces precession, 2pn is a small correction.
This is a fact that we have considered. But from various tests, because of the eigencentricity that the inner binary can reach, they arrive at separation so small that the 2pn term is necessary. Yes. It's a pain in the neck because
I asked him already, and it's making everything 5 times lower, but he says, no, you have to be so.
this is the three-body 2pn of Newtonian, and it requires a very high computational cost.
So does this mean you've actually done it with just the 1pn plus 2.5pn?
Yes.
And it found as a statistical statement that there are qualitative differences between
Yes.
them? That
In
is
most of the tests that they have done, including only 1pn, the dynamics is completely different, of course, because the chaoticity. But we have a problem that says that at a point, one of the components of the inner binary is ejected because of a strong interaction that doesn't happen with the 2pn terms.
I guess I don't understand that because the majority of times the mutual inclination between your inner binary and the tertiary is not going to be such that the cosine mechanism is going to drive you to a very high eccentricity. Just statistically, that's not going to be the case.
Okay.
So does this mean that you're choosing particular initial relative orientations
Yes.
so that you are driven to a very, very high eccentricity?
Yes.
Are you including the fact that the outer object is going to continue to be dragged in by interaction with the star?
Yes. I just come to this point.
Okay.
So these two terms, and of course we have to add this because it's the first order at which the gravitational waves enter the dynamics. In addition to the simple three-body dynamics, we have to consider the stellar environment. Okay. In particular, we have to consider that there are a distribution of stars, so we have a bulge potential. That for now we choose to be spherically symmetric. We plan to introduce some other kind of potential. But most important, we have to take into account the stellar hardening. Stellar hardening, just this morning Alberto explained us something. They can be represented by simple equation. In which the evolution of the same major axis and the centricity is linked to the stellar distribution, rho and sigma, the density and the velocity dispersion and the influence radius. And these h and k are just numbers, as Alberto explained this morning. However, these are orbit average equation, and it's not very straightforward to include this kind of dynamics into a direct integrator. So to overcome this problem, we have decided to introduce a fictitious force requiring that its orbit average effect match exactly this one.
I'm sorry to interrupt again, but do you also include the change in the inclination of the orbit of the tertiary?
No. I didn't include this effect, but it's a point of the referring report that we have received. Yes. And yes, we know that this effect is present, but I found an article of Merit, 202, and another from Totti, Cesana, and Guandres, yes, in which for a spherically symmetric bulge that is not rotating, this effect can be important at much for 10 degrees of the change of the orbital plane of the binary. So, for the most part of the parameter space in the inclination,
Yeah.
this has a minor effect. But of course, if you consider a more complicated potential, that, for example, an axis symmetric potential, this effect can be much higher. And of course, we have to consider the variation in the inclination because it's crucial in the dynamics of the triplet. Yes. So we have to think about it.
Okay.
The fictitious force that I have in mind is this, where the quantity I and D are those who are tuned to match the evolution predicted by the orbit average equation. In this plot, you can see that we have a fairly good agreement. The red dots are the result of the simulation using this force, while the blue lines are the result of the integration of this equation above. So, putting this thing together, I have some sample to show you. For example, in this one, we shows a very high eccentricity, 89 degrees, sorry, inclination, 89 degrees, with the parameter on the right. And you can distinguish at least three. This is a plot in which we have the relative separation of each pair of the body versus time. You can distinguish almost three phases. The first one, in which the third black hole sinks towards the inner binary because of dynamical friction. That is a simple Chandrasekhar formula. Now, at a point, the binary actually binds, the third body actually binds to the inner binary, this region there, where you can see the drop. And this is the start of the hardening. You can see that there is no effect on the inner binary here.
Why did you pick up exactly 89?
Because it's the most favorable configuration for the cosine double oscillation.
To appropriate orbit.
No, 89 is almost.
Yes, 89.2.
Okay. At a point where the third black hole arrives close enough to the inner binary to excite the cosine double oscillation, and they become stronger in amplitude and intensity until the inner binary merges because of the high eccentricity that we were excited. So we have a case in which this mechanism can work. In this second example, we choose a slightly lower inclination. We see that the first part of the simulation is quite the same as the previous. But the eccentricity that is excited is fewer. You can see that the minimum separation is there. First one. Sorry. It's almost at 10 to the minus 2, lower than 10 to the minus 2 parsecs. And this is lower. So, there is not enough time to the inner binary to correction for this mechanism, but the triplet passes from the hierarchical configuration to a chaotic configuration in which we have essentially the ejection of one body and an exchange. So the new binary now become the M1 and M3. However, the dynamics of the exchange is very, very rich, as you can appreciate from this zoom. And also the orbit presents a very messy aspect. Okay. So the next steps that we have in mind are essentially 4. We have to define a parameter space that is astrophysically and cosmologically motivated to determine some initial condition. So, motivated initial condition means that we don't consider black holes of 1 solar mass because we have massive black holes. So, initial condition motivated. The parameters that involve are, of course, the masses of the black holes, but we have to take into account other parameters. The inclination that is crucial. Not all range of inclination can produce this process. Also the eccentricity. Because the time scale or the causality mechanism is strongly related to the eccentricity, and also the higher order terms of the causality mechanism, the optical term, for example, are generated by the eccentricity of the outer binary. Another parameter that is important is the time delay that pass between the first merger of galaxies that form the binary and the second merger that form the triplet. Because it's essentially tell us the dimension of the inner binary, so its semi-major axis, but also how much stellar mass is ejected by the inner binary because of the hardening process. So how the stellar distribution is modified by this interaction. Once this parameter space is defined, we plan to systematic survey this one, and hopefully in 2-3 months we hope to complete the simulation with the appropriate computational thing. Then, what is interesting is coupling the result of the simulation to a cosmological merger tree. Plus a semi-analytical model that is used to populate the halos of dark matter. The merger tree is pure dark matter from simulation, and use a semi-analytical model to populate each halos by galaxies. And this is important because it gives the statistical significance of each part of the parameter space that we have prepared. At last, and maybe the most important, is the computation of gravitational waveforms. As Alberto explained this morning, this is very important because the eccentricity can change in a very dramatic way the signal of gravitational waves, but also the evolution of the stellar environment is responsible for this modification. And so for PTA, also for ELISA, it is important to have a template that can represent this kind of sources with very high eccentricity, maybe chaotic interaction, exchanges, event, and so on. So I am quite quickly, I finish if you want to ask questions.
simulation of this?
It depends. For example, this one, 3 hours
Yeah.
on a desktop computer.
With 2 p.m.
It's weird.
And
This
so-
one, like 18 hours.
So the 2 p.m. is because of the simplicity you were saying?
Yes, because the pericenter separation is very small for 0.9999. It's a bit.
Which integrated skew
Is a bullish store integrator that have a higher accuracy. Is a sort of Runge-Kutta integrator very strong.
It's extrapolation method, right?
Sorry?
It's Bullish story is extrapolation method.
Yes.